Hello everyone, welcome to Mostly Math. Today we are going to look at the following series here. Sine x plus sine 3x over 3 plus sine 5x over 5 plus sine 7x over 7 plus the rest of the infinitely many terms, the odd terms of course. I am making this video because I saw the series summed on a video by Dr. Payam. Excellent channel, I would definitely recommend. I will put a link in the description to that video since it's heavily inspired by that video. In this video, Dr. Payam evaluates the sum by writing sine x equal to 1 over 2i e to the ix minus e to the minus ix and performing some manipulations on the complex exponentials using some identities involving integrals and so forth. In this video, I am just going to consider, e to the ix. There's going to be some other constants, picking out the odd terms, of course, and then at the end, I'm going to take the imaginary part of the results to get sine x. A few comments about the sum. So, like Dr. Payam points out, you can actually recognize this as a Fourier series since you know that this is equal to a constant, which we will actually derive later in the video. From the Fourier analysis perspective, you can easily scale it to know that this is one of the fundamental Fourier series for the square wave. So if we have a periodic repeating function that goes, some constant, 0 for a while, and then it goes back to the constant again, repeats indefinitely. This can actually be represented by the following series. Obviously, we are going to not be concerned about any issues with convergence here, and there are more rigorous ways to derive the sum. This is just an elementary method of deriving the Fourier series. Let's begin. First, we are going to consider e to the I of all of the odd terms. So, we have sum and going from 0 to infinity, e to the I 2n plus 1 x. Notice that the imaginary part of the sum is the same thing as the sum that we have before us. Let's begin. Okay, people. So if we have this sum, the first thing that we want to notice is we can actually write this as, you need the scaling coefficients 2n plus 1. We are going to write this as e to the ix to the odd power, for reasons which we'll see momentarily. We have e to the ix all to the 2n plus 1 power, and we're dividing by 2n plus 1. This is important because we can recognize this Taylor series immediately as the inverse hyperbolic tangent. In particular, we know that tan h inverse, or tanh inverse of x, is equal to the sum as n goes from 0 to infinity of x to the 2n plus 1 over 2n plus 1. So we see that our series is the inverse hyperbolic tangent with x being replaced by e to the ix. So far, what we've done is pretty cool. We look at the complexified version of the series. Note that the imaginary part is simply the imaginary part of the inverse hyperbolic tangent of e to the ix. The next part is, how do we evaluate this weird-looking expression? Well, we're going to use the same identity that Dr. Payam did. It's actually just telling us that tanh inverse of x is equal to 1/2 log of 1 plus x over 1 minus x. This is a fundamental formulae for the inverse hyperbolic tangent. I'm not going to derive it here. It's in every table of mathematical functions since time began. So we can now just write this 1/2 log 1 plus e to the ix over 1 minus e to the ix. And now all we have to do is write this strange combination of e's and ix's in terms of an r e to the I theta form, or convert it to polar so we can take the logarithm of it easily. Well, thankfully this is pretty easy. So we are now going to note that the thing that we want to take the logarithm of, 1 plus e to the ix over 1 minus e to the ix, if we multiply by e to the minus ix over 2, which is a pretty standard trick when you're confronted with these sort of expressions, multiply top and bottom by some complex exponential until something that you recognize pops out. E to the minus ix over 2, and we have 1 minus 1/2, which is 1/2, so e to the plus ix over 2 here, divided by e to the minus ix over 2 minus the same thing here. And from here you can probably see where I'm going with this. We can just note that this looks awfully lot like a tangent function, or as we're going to see in a moment, a cotangent function, since this is just 2 times cosine x over 2, and the bottom is simply 2i, minus 2i rather, times the sine of x over 2. So I just canceled the 2's in my head. There's a 1/2 here, and there's also a 2 here, of course. There's a 2 here and a 2 here. I just canceled them both before writing them down. We could recognize this as I cotangent x over 2. Note how we got a half angle identity for free, basically. I didn't have to use any other trig identities to get this, just multiplying by complex exponentials. So back to our main result. The sum that we're looking for is just equal to 1/2 log of I cotangent x over 2, which we can easily take the logarithm of because we already have this converted to polar form by noting that I is simply e to the I pi over 2, of course. Yeah, it's making sure that I have this in the form that I want it. Obviously, we are choosing the principal branch of the logarithm here. That's normal. Obviously, there's some ambiguity there. I'm not going to cover that in this video. I don't care. So now we just distribute the logs since we know that we can do that. Our final result is now 1/2 log of cotangent x over 2. And now we have the I pi over 2 here being multiplied by 1/2. So it just becomes I pi over 4. And now we actually have the result that we want, which is the imaginary part. We also get another result for free. So I'm just going to erase one of these lines here and celebrate. I need more space. Need more space. So from this result, just comparing imaginary and real parts. So look at this expression up top. We have e to the I stuff. So we look at the imaginary part, will be the sine series, what we want, pi over 4, a constant, just like I promised you. And without doing any extra work, we actually get another Fourier series. We get the cosine series, which is the real part of this, equal to this weird function here. So we now have that original series is equal to pi over 4, and we get another series for free equal to this strange combination of logarithms and cotangents. log cotangent of x over 2. And this is the square wave. Like I mentioned in the introduction, there's some question about the units, the length of the square wave. I believe this is a square wave of length 1. And this function I have numerically verified by plugging it into Wolfram alpha. It does seem to represent this function over a certain range. I don't know much more about it besides what I've derived here. This was a very surprising result to me. I've never seen this. But I believe that this method is superior to the method presented in the video from Dr. Payam, because not only do I obtain the main result with using less algebraic steps, using the same identities, I also get another series completely for free. So I hope this illustrates the power of doing some manipulations on e to the I f of x instead of writing, sine of f of x is equal to 1 over 2i e to the I f of x minus e to the etc. If you can, it's always good to write it in terms of e to the I something and then perform your manipulations, take the imaginary part at the end. I think that's always the way to go. I've never encountered a circumstance where it was more difficult. Because if you look in Payam's video, he does very similar manipulations to the complex exponentials, but with some signs changed around, so it's like double the work for half of the result. And if you enjoyed this, want to see more math, please subscribe. I'll see you next time.